So again, ladies and gentlemen, I strongly recommend that you memorize these basic parent functions in table 2.2 and section 2.6. All right, just make sure you're familiar with what types of graphs these basic functions produce. Okay. All right. All right, the first thing we're going to look at is what is called a vertical translation. How can we cause a graph of a parent function to be shifted upwards or downward? Well, we're going to have to tweak the definition in order to do so. So we'll look at vertical translations here. All right. Vertical translations. Suppose y equals f of x is some function, and let's suppose that k is some positive real number. Then the graph of y equals f of x plus k is going to be the graph of f of x shifted upwards k units. So just by adding a positive real number to a function to form a new function, the graph of the new function will be the original function or the parent function shifted upwards k units. In a similar fashion, the graph of a new function y equals f of x minus k is going to be the graph of f of x shifted downward k units. Okay. All right, so that's how we can induce vertical translations for the graph of a basic function, is to form a new function by adding a positive real number to the function or subtracting a positive real number from the function. The net effect is that it causes the graph to be shifted upwards or downwards. Okay. All right, any questions about that? All right, let's go back to our textbook now. And let's take a look at what's going on here. All right. First of all, they took the basic quadratic function, f of x equals x squared. They put some nice values of x into the function to generate corresponding output y values. So what we've accomplished here is we've generated 7 ordered pairs. They plotted all these 7 ordered pairs and generated a black graph, which represents the graph of the basic quadratic function f of x equals x squared. And there's the graph. It's the black graph. Then they form a new function called g of x by taking f of x and adding 2 to it to produce the new function called x squared plus 2. So how is the graph of g of x now going to compare to the graph of f of x? Well, what happens to the y coordinates of f of x when you form this new function g of x, which is f of x plus 2 or x squared plus 2, is all the y coordinates have 2 added to them. So now if we plot these new 7 ordered pairs where we still use the x column as the x coordinates, but now the y coordinate column is going to be this column here. So when you plot these new ordered pairs and put a smooth curve through them, you'll get the graph of g of x, which is denoted here in red. How does the graph of g of x compare to the graph of the basic parent function, quadratic function f of x equals x squared? What happened to the basic graph? Well, it appears that the basic quadratic functions graph got shifted upwards 2 units. Okay. Notice the shape is preserved. For that reason, we refer to this translation as a rigid transformation in the sense that the shape is preserved. It's just that the graph has been shifted upwards 2 units. If you form a new function h of x, which is f of x minus 4, what happens to the y coordinates of f of x is they all have 4 subtracted off from them. And when we plot these new 7 ordered pairs, still using the x column for the x coordinates, but using the last column for the new y coordinates, you would generate this blue graph, this blue parabola opening upwards. That would be the graph of h of x. And notice the blue graph, where h of x is graph, compares to the original function graphs f of x, and that it got shifted downwards 4 units. Okay. Any questions about that? All right. So that's how we can induce a vertical translation, either up or down, either adding a positive real number to a function or subtracting a positive real number from the function. All right, horizontal translations are next. Horizontal translations. So the graph of y equals f of x plus h, where h is some positive real number, is the graph of f of x shifted h units to the left. H units to the left. Now it seems strange because we're adding a positive real number to the argument of the original function. Seems like the graph would get shifted h units to the right, but it's just the opposite. The graph of f of x gets shifted h units to the left. In a similar fashion, the graph of y equals f of x minus h is going to be the graph of f of x shifted.
Now a 38-year-old male with a history of diabetes. Sorry.
To the right. This will cause the graph of f of x to be shifted h units to the right. Okay. So that's how we induce a horizontal translation in a graph. Notice the difference here. To induce a vertical translation, we add a positive real number or subtract a positive real number from the function. To produce a horizontal translation, we are either adding a positive real number or subtracting a positive real number from the argument of the function. That's the difference. All right. Any questions about that there?
You heard what I said about finding the pancreatic duct, right? Because I really want to make sure you know that I would train the anastomosis.
Somebody's
Whose audio is that?
audio gone. Madison, is that yours? Good. All right. Let's go back to the textbook. Okay, now example number 2. This is in section 2.6 here. Okay, these are just more, example 1 is just illustrating vertical translations that it could occur. So if you take the graph of the basic absolute value function, form a new function g of x by subtracting 3 from that basic parent function, that causes the graph of the absolute value function, a v-shaped graph, to be shifted downwards 3 units. Notice that. Next one, if you take the basic cubic functions graph, form a new function called h of x by adding 2 to that basic function f of x equals x cubed. That causes the graph of the cubic function to be shifted upwards 3 units. Okay. All right, example 2 here. Suppose that we use the basic quadratic function f of x equals x squared, and the graph of that function is shown in gray here, which is your basic parabola that opens upwards where the lowest point on the parabola is at the origin. Suppose we form a new function called g of x, which is going to be f of x plus 3. which would give you this new function x plus 3 squared. Well, the graph of g of x now is going to be this blue parabola opening upwards, which is the gray graph shifted 3 units to the left. Notice 3 units to the left, x plus 3 units to the left, not to the right. Okay. All right. Okay. All right. Suppose we look at skill practice 2. What would the graph of g of x equal to the absolute value of x plus 2 look like? How would it compare to the basic absolute value functions graph? Well, the basic absolute value functions graph is in gray. That's just f of x equals the absolute value of x. We form a new function called g of x, which is going to be f of x plus 2. The graph of this new function g of x here is going to be the gray V-shaped graph shifted 2 units to the left. Okay, 2 units to the left. All right. Well, ladies and gentlemen, we can have multiple translations that can occur. For instance, if we look at this one here, example 3, section 2.6, page 232. If you look at the graph of the basic square root function, f of x equals square root of x, that is going to be this graph here in gray. And that was from that aforementioned table that opened up section 2.6. So just become familiar with those basic parent functions above there in that table 2.2. All right, so if we form a new function from our basic square root function called p of x, which is going to be f of x minus 3 minus 2, what type of translations is our basic parent function's gray graph going to experience when we go to the graph of this new function called p of x? Well, first of all, the gray graph is going to be shifted 3 units to the right. Okay. And then it's going to be shifted 2 units downward. So the graph of the basic square root function is going to be shifted 3 units right and then down 2 units. So you can pick a point on the gray graph and shift it 3 units to the right, like this point right here, 1, 2, 3, and then down 2, 1, 2, plot the point. You can do that with this point, 3 units to the right, 1, 2, 3, and then down 2 units, 1, 2, plot the point. You now get to this blue curve, which is the graph of this new function p of x. That illustrates the 3 unit to the right shift and the 2 unit down shift of the original basic square root function graph. All right. So far, all of these translations here have been, they have been rigid transformations in the sense that the graph shape is preserved. It's just that the graph is being literally moved right or left, or up or down. Here's another example. Again, if we build a new function up from our basic square root function and into this function q of x, how is the graph of q of x going to compare to f of x equal to just the square root of x, whose graph is shown in gray here? Well, what kind of transformations have occurred to the basic square root function? Well, first of all, we're evaluating f of x at f of x plus 2. That's going to cause the gray graph to be shifted 2 units to the left. And then we're subtracting off 5 units from f of x, which causes the graph to be shifted downwards 5 units. So the gray graph is going to be shifted 2 units to the left, 1, 2, and then down 5. 1, 2, 3, 4, 5. Plot the point. You could pick another nice point on the gray graph here. Shift it 2 units to the left, 1, 2, and then down 5 units. Negative 1, 2, 3, 4, 5, and there's the new point. Connect the points with a new smooth curve, and you have this blue graph. That is the graph of this new transformed function called q of x, which is f of x plus 2 minus 5. Okay. So you could have a combination of many transformations instead of just one, which is going to, have you adjusting the graph of the basic parent function in many different ways. Those are all called rigid transformations. Let's start looking at what are called non-rigid transformations here. How could we induce a graph of a function to experience a vertical stretching or shrinking? To occur? Well, suppose again we have some function f of x, whatever the function is. Suppose a is some positive real number. If, ladies and gentlemen, a is a positive real number greater than 1, then the graph of y equal to a times f of x is going to be the graph of the basic parent function f of x stretched, we say stretched vertically. Stretched vertically by a factor of a. Okay. So in other words, for any point xy on the graph of f of x, the point x a times y will be a point on the graph of this new function, which is a times y, which is a times f of x. Okay. So in other words, basically put, when you multiply a function by a real number greater than 1, it's going to cause all the y coordinates of the basic function to be basically stretched vertically by a factor of a. That's what's going to happen. So that's going to, give you the effect that the graph has been pulled vertically upwards, right, or stretched vertically upwards. And all right. If, ladies and gentlemen, a is some positive real number between 1 and 0, meaning a is some, positive fraction or positive decimal between 0 and 1, then the graph of y equals a times f of x will be shrunk vertically by a factor.
Can you go down, please?
By a factor of a. In other words, for any point xy on the graph of f of x, this would imply then that the point x ay will be on the graph of the new function a times f of x. Okay. So remember, now a is some fraction, like, let me give an example, like 1/2. Okay. So if you form a new function by multiplying your parent function, your basic function, by 1/2, that's basically going to have all of your y coordinates of the basic function, which causes the y coordinates of the new function to be only half of what they were for the parent function. That's going to give you the illusion that the parent function's graph has literally been shrunk or compressed vertically. Okay. All right, and a good example to look at to experience this phenomena is example 4 in section 2.6 of your textbook. So I've arranged this lecture so that it's in chronological order. So like in your notes now, you might want to say, go over or look at example 4 in section 2.6, okay? Because that's what we're going to do next year. So let's, wait a minute, first of all, do we all have this down or accounted for here? I know it seems like a lot. All right, so let's go over example 4 here. All right, they give us some a base in A of example 4, problem A. They give us the a basic parent function, which is your basic absolute value function. f of x equals the absolute value of x. And they make a table to generate some ordered pair solutions for these functions so we can plot them and graph these things. They chose some nice input values for x and substituted them into f of x. In other words, took the absolute value of all these x input values and generate the corresponding y values, the output values. Plotting these 7 ordered pairs generates the graph of f of x equals to the absolute value of x, which is just going to be this gray V-shaped graph that opens upwards, and notice the lowest point is at the origin here, 0, 0. Suppose we use that basic parent function of the absolute value function to form a new function called g of x, where we multiply the parent function f of x by 2, positive 2. Well, the effect that that's going to have on the graph of f of x is to basically double all the y coordinates. So all the y coordinates get doubled. So therefore, the graph of g of x, which is 2 times f of x, which is 2 times the absolute value of x, is now going to be this graph in red. And notice it looks like the graph in red is the gray graph that's been stretched vertically upward by a factor of 2. Okay, so you can see the vertical stretching that occurs with our basic gray graph, f of x equals the absolute value of x, and it becomes this red graph when you multiply f of x by 2. In a similar fashion, we form a new function h of x by multiplying the parent function f of x by 1/2. The effect it's going to have is to have all the y coordinates. So all the y coordinates are cut in half. So now the graph of this new function h of x is going to be this gray graph, okay, that has basically been compressed vertically downward or shrunk downwards vertically, and it becomes the blue graph here. That would be the graph of this new function called h of x. So you can see the vertical stretching that can occur, or the vertical compression or shrinking that can occur if you just multiply a function by either a real number greater than 1 or by some real number between 1 and 0. Okay, so example 4 illustrates this nicely here. Any questions about vertical stretching or shrinking that could occur and how to induce it? All right, next we want to look at horizontal shrinking and stretching that could occur with a graph. All right, so horizontal stretching, shrinking that could occur with a graph. How do we induce it here? Well, again, we'll start off with some basic parent function, f of x, and we'll let a be, again, some positive real number. If Lezman a is greater than 1, some positive real number greater than 1, then the graph of this new function, y, which is going to be not a times f of x, but f of a of x. In other words, we're forming a new function from our parent function f of x by evaluating our parent function at a new argumentative input value called a times x. And again, a is some real number greater than 1. So what happens? Well, the graph of this new function is going to be the graph of the basic parent function f of x that will experience a horizontal shrinking. So the graph of f of x is going to be shrunk by a factor of 1 over a. If a, on the other hand, is a positive real number between 1 and 0, some fraction or decimal, then the graph of this new function, y equals f of a times x, is going to be the graph of f of x stretched horizontally. Stretched horizontally by a factor of 1 over a. Okay, 1 over a. So in general, it works like this. So for any point xy on the graph of f of x, this would imply then that the point x over a comma y is a point on the new function f of a of x. Okay. So what's really going on here? If a is some positive real number greater than 1, let me give you an example. Suppose a was like 2. Well, ladies and gentlemen, what's going to happen to the x coordinates? The x coordinates, if a is 2, the x coordinates are going to be what? Cut in half. You agree? The x coordinates will be halved. That's going to cause the graph to experience a horizontal shrinking, or the graph's going to be compressed inward, horizontally inwards from both sides. If, on the other hand, a was, let's say, 1/2. Let's say a is 1/2. Then the x coordinates of the new transformed function is going to have x coordinates that are going to be x divided by 1/2. But x divided by 1/2 is really going to be 2 times x. So when you form a new function f of a of x, and a is like a fraction between 0 and 1, like 1/2, now the x coordinates are going to be doubled. That's going to cause the graph to experience a horizontal stretching. So the way to remember it is this: vertical stretching and shrinking is just the opposite of horizontal stretching and shrinking. If a is greater than 1 and you multiply the function by a, the graph is stretched vertically by a factor of a. If a is some real number between 1 and 0, multiply the function by a, the graph is shrunk vertically by a factor of a. If, however, a is greater than 1 and you form a new function f of a of x, then the graph of f of x is going to be shrunk, not stretched, shrunk horizontally by a factor of 1 over a. If a is some fraction between 0 and 1, it's just the opposite of what it was for a vertical stretching, compression. Because if a was some fraction between 0 and 1, we multiply a function by a, we would have a vertical compression taking place. But it works just the opposite in the horizontal sense. If you form a new function f of x, a is some fraction between 0 and 1, then the graph will experience a horizontal not shrinking or compression, but it will experience a horizontal stretching. Okay, so horizontal stretching and shrinking works just the opposite of vertical stretching and shrinking. And notice for vertical stretching or shrinking, the factor is outside the function. For horizontal stretching and shrinking, the factor a is a part of the argument, the input value into the function. That's the difference. All right, so let's go over example 5. By the way, all of this is summarized in a table in your book here, everything I'm going over here. All right, so let's look at example 5 here. Suppose they give us the graph of some function f of x. It's denoted by this, black graph right here, these lines. And suppose they want us to form a new function, which is f of 1/2 of x. So I have a question for you. First of all, is this going to be a vertical change in the shape of the graph or a horizontal change in the shape of the graph? What do you think it's going to be? Vertical or horizontal change? What's that?
Horizontal?
Yeah, it's a horizontal change in the graph because we're multiplying the argument of the function. I'm sorry, I'm looking at B here. All right. We'll do B, then we'll do A. So B, yes, f of 1/2 of x, we're multiplying the argument of the original parent function x by 1/2, which is going to cause the graph of f of x to experience a horizontal shrinking or stretching. What do you think? Shrinking or stretching here?
That one is stretching for B.
Yes, this will be a horizontal stretch. Okay. For B. So let's go down here and let's take a look here. Okay, so let's try to graph this new function called f of 1/2 of x here. So notice, ladies and gentlemen, that our a is really 1/2. Okay, to form this new function f of a of x. So a is 1/2, and that means that all the y coordinates, okay, are going to be horizontally stretched by a factor of 1/2. Because if you look at like the point -4, 2, which is on the graph of the original function f of x here, -4, -2 right down here, this point, its x coordinate is going to be -4 divided by 1/2, which literally becomes -8 now. So therefore, this point -4, -2 on the graph of the original parent function now becomes the new point -8, -2 on the graph of this new function called f of 1/2 of x. And the point -2,4, which is on the graph of the basic parent function right here, -2,4, what happens to its x coordinate? Well, the x coordinate is divided by 1/2, which really means it's multiplied by 2. So now the x coordinate becomes -4. So therefore, this point -2,4 becomes the new point -4,4 on the new function's graph, f of 1/2 of x. Finally, to -2, this point down here on the original function's graph becomes the new point for -2, because again, the x coordinate is divided by 1/2 because a is 1/2, right? And so the x coordinate now becomes 4. So 4 and -2 would be a point on the new function's graph, this red graph over here. So you can kind of see, it's kind of like, you know, you grab a hold of this black graph here and you kind of pull it away from, you pull it to the left and you pull it to the right. And that basically causes the graph to experience a horizontal stretching, okay, in the horizontal. All right. Now let's look at function a here. We take a basic parent function and we form a new function, which is f of 2 of x. Well, the graph of f of 2 of x is going to be the graph of f of x that has been compressed by a factor of what? Of 1/2. So a is equal to 2 here. That means all of the x coordinates of the points on the original function's graph are going to become halved. Okay, they're all going to become halved to give us the new points on the graph of this new function called f of a of x. And so you can see how all the x coordinates have been halved. And plotting the new graph here in blue, you can see indeed it has been, it's like this original function's graph that has been basically pushed in from the right side and pushed in from the left side, experiencing a horizontal compression. Okay. All right. Okay. So those are non-rigid transformations when you start stretching or compressing a graph vertically and or horizontally, because you're changing the shape of the graph. Okay. There's a couple of other things that could happen to a graph. We could induce the graph of a parent function to experience what's called a flip or a reflection about an axis. Okay. So we will look at what are called reflections about the x or y-axis. And again, we'll start off with some basic function, y equals f of x. Then we say the graph of this new function, y equal to the negative of the original parent function, f of x, is going to be the graph of y equals f of x reflected about the x-axis. So it's going to be reflected about the x-axis. So basically what's happening here, for every point xy on the graph of the basic parent function f of x, this would imply that we now have a point x negative y on the graph of the new function of y equal to the negative of f of x. So envision this. If we have the graph on f of x, which is like some point xy, well, as I'm on now, the new point on the new function's graph is going to be x negative y, which you can clearly see that this point here has literally been reflected about or over the x-axis. Has been reflected. All right. All right. Furthermore, the graph of this new function y equals f of negative x. What if we put the negative sign inside the function? In other words, attach it to the argument of the function as opposed to having it outside the function. Well, the graph of this new function is going to be the graph of f of x reflected about the y-axis now. Now the graph is going to experience a reflection about the y-axis. Because here's what's going to go on here. For every point xy on the graph of f of x, on the new function's graph, the point will become negative xy. This will be a point on the graph of the new function f of negative x. So graphically speaking, if we have some point xy on the graph of our original function, well, the new point on the transformed function is going to be over here, negative xy. And so you can see that the point xy has been flipped about the y-axis. Flipped about the y-axis. Okay. So that's how we can induce reflections about an axis, is by either multiplying a function by -1 or multiplying the input argument of a function by -1. Okay. When you got the negative sign outside the function, the reflection is about the x-axis. When you got the negative sign inside the function as part of the argument of the function, the reflection is about the y-axis. And example 6 will enable us to experience some of these reflections that could occur. So example 6 in section 2.6 now in your textbook. So let's go to example 6. Here it is. All right, so ladies and gentlemen, I give you the graph of some parent function f of x. It is this graph that is shown here. And they want us to form new functions and then graph them. The first new function they want us to form is going to be the parent function multiplied by -1. So I have a question for you. If I form this new function y is equal to the negative of f of x, how is the graph of this new function going to compare to the graph of the original parent function? Is it going to be reflected about the x-axis or the y-axis? Well, because we got the negative sign outside the function, that's going to cause all the y coordinates on the original parent function's graph to take on the opposite sign. So therefore, this point 0, -1 now becomes the point 0, +1. This point here, 3, 2, now becomes the point 3, -2. This point 4, 2 now becomes the new point 4, -2. This point 5, 0 remains as 5, 0. And we have the graph of the new function in blue here, which is our new function y equal to the negative of f of x. Questions how we induced a reflection about the x-axis. You can think of the x-axis as being kind of like a mirror here. Each point of this black graph here looks in the mirror and sees itself behind the mirror. Sees itself behind the mirror, okay? Suppose we take the parent function and form a new function called y is equal to f of negative x. Now the negative sign is part of the argument of the function. So that's going to cause the graph of the parent function to experience a reflection about the y-axis. So here it is. Here's the graph of your basic parent function f of x. So now all the x coordinates on this black graph are now going to take on the opposite sign. So like the point here, 3, 2, the x coordinate goes from being positive 3 to becoming negative 3. So negative 3, 2 is the point that lies on the graph of the new transform function. 4, 2 now becomes the new point, negative 4, 2. The point 5, 0 has the x coordinate taken on the opposite sign. So negative 5, 0 is found now on the graph of the transform function. And notice that this point 0, negative 1 happens to sit right on the axis of reflection, which is the y-axis. And so that its reflection would still be 0, negative 1. And you have the red graph here. The red graph represents the original parent function's graph that has been reflected about the y-axis. Is this making sense, the reflections here? Reflections. By either multiplying a function by negative 1 or multiplying the argument of a function by negative 1. Notice the difference that it causes on the graphs here. All right. Okay, ladies and gentlemen, on page 236, there is a table that basically summarizes everything I've just gone over. So I would become very familiar with this table here. This summarizes all the transformations that we can, inflict on a basic parent function. We can cause the function to be shifted upwards or downwards, right or left. We can cause the graph to experience a vertical stretching or shrinking, or horizontal stretching or shrinking, or we can cause the graph to experience a reflection about either the x-axis or the y-axis. It's all here in this table. This basically encapsulates the entire section. Table 236 on page 236. All right. All right. What if we have a whole bunch of transformations that occur with a function instead of just one at a time? Well, if we have a whole bunch of them, this table here on page 236, the bottom of page 236, think of it as being kind of like the order of transformations, just like we have the order of operations in math. Think of this as being like the order of transformations. Ladies and gentlemen, if your function it has experienced many different transformations, you always want to deal with them in this order. You always want to look and take care of any horizontal translations or shifts to the right or left that have occurred. Then you want to deal with any sort of horizontal and vertical stretching or shrinking that may have occurred. Then you want to deal with any sort of reflections that may have occurred about the x-axis or the y-axis. And last but not least, you want to deal with the vertical translations if your graph has been shifted upwards or downwards. So notice the order in which we tackle the myriad of transformations that could be exhibited by a function here. So we deal with horizontal translations first, horizontal, vertical, stretching, shrinking, reflections of any kind, and the vertical translations. I would become familiar with these order of transformations here, okay? Because we want to take them in the order in which they suggest here. All right, so here, ladies and gentlemen, is a function in example 7, section 2.6, page 237. I have a question for you. What was the basic parent function that they used to build up to this complicated function called n of x? What basic parent function did they use? F of x equals what? Anybody? Was it the basic linear function f of x equals x? Yeah, it was your basic quadratic function, f of x equals x squared. And then they've taken that basic parent function, f of x equals x squared, and they built it up into this complicated function, n of x, which is still a quadratic function, don't get me wrong. But what kind of transformations have occurred here? Let me ask you this. Has there been any horizontal translations or shifts to the right or left? And if so, what indicates it in the definition of this new function? Any horizontal translations that have occurred? Anybody? Any horizontal translations that may have occurred? Well, in fact, ladies and gentlemen, what I'm going to have you do here for classwork number 1, I want you to indicate all of the transformations that have occurred to f of x equals x squared in building up to this function here, n of x. Go ahead on a piece of paper, classwork number 1. Today is October 12th. I want you to indicate in order, according to the order up here in this table. I want you to indicate in order all the transformations that have occurred to f of x equals x squared. Go ahead and do that. I'll give you a couple minutes to maybe look back through your notes there to try to come up with all those transformations. Okay, let's look at the transformations that have occurred here. Has there been any horizontal transformation? And if so, what in this function's definition indicates that?
There was a horizontal shift 2 units to the right.
2 units to the right. Okay, good. What indicates that?
The x minus 2.
Yeah, exactly. See the x minus 2 inside the parentheses here? That means we took f of x and formed a new function called f of x minus 2, which means the graph of the original parent function f of x has experienced a horizontal shift of 2 units to the right. You are correct there. All right, good. Any horizontal or vertical stretching or shrinking that has occurred?
You have a vertical shrink of -1/2.
Okay, yeah, do away with the negative sign. Just say
Just
we had a
1/2.
vertical shrinking of a factor of 1/2. Exactly, because they formed a new function by taking f of x and multiplying it by 1/2. You're correct. There was a vertical shrinking by a factor of 1/2. Notice there was no horizontal shrinking or stretching because x, the argument, the input value of the function, is still multiplied only by 1. Okay, so no horizontal shrinking or stretching has occurred, but because we're multiplying the function by 1/2, yes, a vertical shrinking has occurred. All right, any sort of reflections about the x or y axis, x and or y axis? Any reflecting about any of the axes? Well,
The
notice-
-1.
Yeah, because we're multiplying the function by a negative here, or by a -1 technically, that would cause the graph of the basic parent function to be reflected about the what axis? At the negative
The
side?
x.
The x-axis, that's right. It's a reflection about the x-axis. Finally, are there any, and notice there's no reflection about the y-axis because the argument of the function x has not been multiplied by x. Only the function's been multiplied by -1. The argument x has not been multiplied by -1. All right, any vertical translations? Any vertical? What does this +3 out here indicate? That means the function.
Up 3.
Yeah, that means the function f of x's graph has been shifted upwards 3 units. Okay, so let's take a look here. This is really something nice your author done here, ladies and gentlemen. Not only do they indicate all of the transformations that occur, but they take the transformations in order to graph the new function n of x. They take them in specific order. First of all, what is the graph of the basic parent function y equals x squared? It's the basic parabola in gray here. All right. Then they form a new function, which is f of x minus 2, which is x minus 2 squared. That causes the basic parabolic graph in gray to be shifted 2 units to the right to now become the blue graph. Then they take this function y equals x minus 2 quantity squared, and then they multiply it by 1/2 to form this new function, which is 1/2 times x minus 2 squared. That causes the blue graph to experience a vertical shrinking. So this blue graph is shrunk downwards or pushed or compressed down closer to the x-axis. In other words, the y coordinates of all points on the blue graph have been halved. And that's why you now have this red graph. All right. Then they take this function y equals 1/2 times x minus 2 squared, and the next transformation they subject it to is they multiply it by a -1. Well, that causes, therefore, the red parabolic graph to be reflected about the x-axis. So every point's y coordinate on the red graph now takes on the opposite sign. Then we get the graph, the green graph here, which is the red graph reflected about the x-axis. Finally, they take the function y equals -1/2 times x minus 2 squared, and they form a new function by adding 3 to that function. That causes the green parabolic graph to be shifted upwards 3 units. And finally, ladies and gentlemen, the black parabola here represents the graph of our final complicated function n of x, which is -1/2 times x minus 2 squared plus 3. Do we understand how all these transformations have been displayed in stages or steps here? Okay, in the order that was suggested above. All right. Okay. Let's look at example 8 here. Notice, ladies and gentlemen, they have a a square root or a radical function here. And what would be the basic parent function that spawned this complicated function? Well, it would be your basic square root function. F of x equals the square root of x. And then they built this basic parent function up into this complicated function we're looking at for v of x. What type of transformations have occurred? First of all, are there any horizontal translations that have occurred? Because we got x plus 2 here, okay, that means that the graph of f of x has been shifted to the left 2 units. Secondly, notice that there's no horizontal stretching or shrinking that has occurred because x is still multiplied by 1. The function outside is multiplied by 1. But were there any reflections? Yes, there were. Notice the argument x is multiplied by a -1, which means the graph of f of x has been reflected about the y-axis. Furthermore, the basic function f of x's graph was multiplied by -1. That means the graph of f of x is also reflected about the x-axis. And there you go. Those are all the transformations. So let's take them in order and try to graph this new function called v of x. First of all, the graph of the basic square root function is in gray here. Then they build the function up into the new function, which is f of x plus 7, which is the square root of x plus 7. I'm sorry, the square root of x plus 2. That causes the gray graph to be shifted 2 units to the left. Shape is preserved. Then they build this new function up, y equals the square root of x plus 2, into the new function, which is the square root of -x plus 2. Well, now by putting a negative in front of x, the argument, that causes the blue graph to be reflected about the y-axis. So all the x coordinates of the points on the blue graph now take on the opposite sign, and we get the red graph in doing that. Finally, building the function y equals the square root of -x plus 2 up into this function, the negative of the square root of -x plus 2. By multiplying the previous function by a -1 now, that causes the graph, the red graph, to be reflected about the x-axis. So every y coordinate of every point on the red graph now takes on the opposite sign. Hence, we now get the graph in black. And ladies and gentlemen, the graph in black is the graph of our final function called v of x. Is this making sense here? How taking these transformations in order, we can graph a complicated function from a basic parent function. All right, let's go down to problem 63. Let's go down to problem 63 through 78 in our textbook. By all means, not only would I look at some of these examples and study them in your textbook, but I would also try to do some extra practice problems at the end of each section that I do cover, in addition to what I assign on Alex. Ladies and gentlemen, if you need extra practice, it's all waiting for you. And I give you all the solutions to all these problems too. That's the beautiful thing. Okay, now we're not going to graph these functions because we're running out of time. But ladies and gentlemen, I just want you to illustrate to me what kind of transformations have occurred to the basic quadratic function in problem number 63. What has happened to f of x equals x squared? Talk to me about some of the transformations that have occurred. F of x equals x squared. What's happened?
An X reflect?
What's that?
An X reflect?
X reflection, did you say?
Yes.
Yes, because the function has been multiplied by a -1 out here. That does cause the graph of f of x equals x squared to be reflected about the x-axis. You are correct. How about this x plus 2?
Horizontal shift to the left.
That's right. By adding 2 to the argument, that causes the graph to parent function to experience a horizontal translation or shift of 2 units to the left. Notice it's in the opposite direction of that sign always. What does the +1 out here do?
Upward shift 1.
That's right. It causes f of x equals x squared graph to be shifted upwards 1 unit. So there's 3 transformations. We have a reflection about the x-axis. We have a horizontal translation of 2 units to the left, and we have an upward shift of 1 unit. Good. All right. So just by looking at these new functions definitions, you can kind of see like what's been going on. So what kind of transformations happen to the basic absolute value function for number 68? If I had f of x equal to the absolute value of x, what's happened to its graph? Just by looking at this new functions definitions, what's happened?
You got a horizontal left shift,
Yeah, this
vertical
X plus-
translation.
You also have a vertical shrink of 1/3.
Yeah, we got 3 transformations. First of all, x plus 2 means the graph of f of x, which is the basic absolute value function of x, has been shifted 2 units to the left. By multiplying the function by 1/3, that is correct. We cause the graph to be vertically shrunk by a factor of 1/3. And by subtracting 1 from the function, that causes the function to be shifted downward 1 unit. Exactly. All right. So again, there's a wealth of extra practice in here in these sections. If you need extra practice, do some extra practice. I will, I'll give you all the solutions. So don't worry about that. Okay. All right. What if I give you this here to close the door on this section here? What if we use the basic cubic function, f of x equals x cubed? And I want you to write the new transform function that corresponds to these transformations here. So what would this new function g of x look like, ladies and gentlemen, if this is our basic parent function, f of x, which is x cubed, and I induce these 3 transformations, a horizontal shift of 2 units to the right, a reflection about the x-axis, and a vertical translation of 6 units upwards. What would my new function look like?
I just have a question.
Yeah.
Are the bottom ones supposed to be cubed?
Well, the thing is remember, f of x is what? X cubed. Do you agree?
Yeah.
So just follow along what this is saying. So it's saying I take the opposite of my function f of x evaluated at what? X minus 2. So that means I put x minus 2 in for what? X here. So this is going to be the opposite of x minus 2 what? Cubed.
Oh,
And then-
I just blanked out for a second and
Yeah.
I didn't see the cube on the bottom ones and I
Oh.
got very confused for a second.
Yeah,
All right.
no, it is the cubed function because f of x is x cubed, and this is what? F evaluated at what? x minus 2. So x minus 2 goes in here, so it's still cubed. You see that there? Okay.
Yeah, I understand. It's
Okay,
just I
all
thought you
right.
meant that the bottom ones were supposed to be a translated version of the top, and I didn't see the cubed.
Yeah, you're right. It is a little bit weird when you look at this here, because you don't see, wait a minute, I thought f of x is x cubed, and we want to go to a new function like this, but I don't see the cube anywhere. Well, the cube comes into existence by virtue of the fact that we're putting x minus 2 into f of x, which has us cubing x minus 2. Okay. All right, so now that you've seen that one done, this one should be a little easier. Help me to write the function h of x based on this being the parent function, x cubed here. So how would I write my new function h of x? It would literally be what? -4 times what? What's going into x here for f of x? 3x plus 1 is going, drop it in here. So the 3x plus 1 gets what? Cubed. And then we subtract off 2. There you go. So the brand new function, which is -4 times f of 3x plus 1 minus 2, would have to be this new function here, because again, we're feeding off the basic parent function, which is x cubed there. Okay. And of course, you know, you could go on and graph these new complicated functions here after, you know, by shifting the graph of the basic parent function around and transforming the graph based on the transformations that have been experienced there. All right, ladies and gentlemen, that's all I got the time for that section. I mean, we burned a ton of time, but there's a lot going on in that section. So, you know, I mean, Alex may not always be enough, okay? I mean, if you feel like you need extra practice, by all means, go in your textbook, do more problems. Make sure you at least look at the examples. Study the examples in the sections I cover. That's extremely important. That really helps to solidify this better in your mind as to what's going on in these sections. All right, those are keys to success in this course. Okay. All right, so let's close the door on that section 2.6. Now, ladies and gentlemen, we're going to open up section 2.7. And it is entitled The Analysis of Graphs of Functions. That's the entitlement of section 2.7, the analysis of graphs of functions here. Suppose that we have some function at y equals f of x. And suppose, ladies and gentlemen, for every point xy that's on the graph of f of x, there is a corresponding point of -x comma y on the graph of f of x. Then, ladies and gentlemen, we say that f of x is symmetric with respect to the y-axis. Symmetric with respect to the y-axis. Okay? Let's get a visual on what that's trying to say. Suppose I have the graph of some function y equals f of x. Here's the graph. It happens to be a parabola that opens downwards. Okay? For every point xy that lies on the graph, suppose I choose some arbitrary point on the graph xy. Suppose for every point on xy on the graph, suppose there exists a point -x comma y also on the graph. If that's the case, then we say the graph of this function is symmetric with respect to the y-axis. We say the y-axis is an axis of symmetry for this graph. It's kind of like, think of it this way. If this was a piece of paper here, and if I folded this paper about the y-axis, do you agree this point would mesh up perfectly with this point? This point would mesh up perfectly with what? This point over here. This point would mesh up perfectly with what? This point over here. Do you agree? That's to say that this graph is then symmetric with respect to the y-axis. All right. So this is what a graph looks like if it's symmetric with respect to the y-axis. Does that make sense there? All right, if we have some function y equals f of x, and if it's true that for every point xy on the graph of f of x, there exists a point x comma -y on the graph of f of x, then, ladies and gentlemen, we would say f of x is symmetric with respect to the x-axis. And this would illustrate such a scenario. Suppose I have the graph of some function f of x. It looks like this. Suppose I arbitrarily choose some point on my graph called xy. And if it's true that for every point xy on this graph, if there exists a point x -y also on the graph, then we would say that this graph is symmetric with respect to the x-axis. Just think about it. If you were to fold this paper about the x-axis, all these points on this branch of our parabola would mesh up perfectly with all the points on this branch. That's to say that this graph is symmetric with respect to the x-axis. Okay, everybody see that there? X-axis symmetry. All right, so this is what a graph looks like if it's symmetric with respect to the x-axis. This is what it looks like if it's symmetric with respect to the y-axis. Okay. All right. Furthermore, ladies and gentlemen, if for any point x, y on the graph of a function f of x, there is also a point negative x, negative y on the graph of f of x, then we say f of x is symmetric with respect to the origin. Symmetric with respect to the origin. Such a graph that would illustrate that characteristic would be this one here. And this, you might notice, is the graph of the basic what? Cubic function. F of x equals x cubed. For every point xy that's on this graph, there also exists a corresponding point on the graph that is negative x, negative y. And notice I would have to, in drawing a line between these 2 points, I would have to go through the origin. That's why we say this graph is symmetric with respect to the origin here. Okay, if that's the case there. Okay. So that's how you can tell if a graph is symmetric with respect to one of the axes or the origin. So suppose that a typical problem involving this concept would be, if I gave you a problem like this and I wanted you to discuss the symmetry that exists, discuss the symmetry of the function f of x equals absolute value of x. All right, you can do this one of 2 ways. You can graph the function and just look at the graph and just ascertain whether it's symmetric with respect to the x-axis, y-axis, or origin. Or you can do individual tests. You don't even have to graph it. In other words, if you want to test, or let's say, first of all, we want to test for x-axis symmetry. To test for x-axis symmetry is pretty easy. All you do is you replace y with negative y. We replace y with negative y, and then we simplify. And the point is this: after simplifying, if we can get back the original equation, then we would say our graph possesses x-axis symmetry. F of x looks messy. Why don't we replace f of x with y? So let's suppose our function is y equals the absolute value of x. All right, so I'm going to replace y with negative y. Here we go. And then I'm going to simplify, trying to get back my original equation, which is this one here. Well, how can we do that? Well, in order to get back positive y, I would have to either multiply or divide both sides by a -1. So if I did that, the problem is I got to multiply the right side by -1 also. Yeah, I'd get my positive y back. I'd get my positive y back, but do I have the absolute value of x on the right side? The answer is no. And so, ladies and gentlemen, when I replace y with negative y and try to simplify, trying to get back my original equation, I cannot do it. Because I cannot get my original equation back, we would say there is no x-axis symmetry, all right? This graph is not symmetric with respect to the x-axis. Not with respect to the x-axis. Doesn't work. All right, suppose we in B, we want to test for y-axis symmetry. And to do so algebraically, I'm going to replace x with negative x. So negative x goes in for x, and then we're going to simplify, hoping or trying to get back our original equation. So let's do that. Let's take our original equation, which is this, or original function, replace x with negative x. So in goes negative x for x. Now I simplify. When I simplify, can I get back my original equation, y equals the absolute value of x? What is the absolute value of x? I'm sorry, what's the absolute value of negative x?
Just x.
Yeah, isn't the absolute value of any negative number still the same thing as the absolute value of the positive of that number? Isn't that true? So the absolute value of negative x is just what? Absolute value of x. Same thing as the absolute value of positive x. Well, guess what? I got back my same equation. Same original equation. And therefore, we would say that yes, we do have y-axis symmetry here. So it looks like our graph is symmetric with respect to the y-axis. Okay. Finally, to test for origin symmetry. To test for origin symmetry, we do two things. We replace y with negative y, replace x with negative x, and then simplify. So let's take our basic function here, y equals absolute value of x, replace y with negative y, replace x with negative x, and simplify. Well, the absolute value of negative x is the absolute value of positive x. I can get that back, but I still have a negative y out here. If I multiply both sides of the equation by -1 and try to get back positive y, the problem is I would have a negative on the right side. Bottom line, ladies and gentlemen, is I cannot get back my original equation after replacing y with negative y, x with negative x, and simplifying. And so therefore the answer is no. There is no origin symmetry. Okay. Right? No origin symmetry. Now, if you were to take the time and graph y equals the absolute value of x, or if you have memorized the basic parent functions I wanted you to memorize in that table that opened up to section 2.6, we would realize that the graph is the V-shaped graph that opens upwards and looks like this. And you can clearly see that this graph is symmetric with respect to what axis? Not the x-axis. It doesn't have origin symmetry, but it is symmetric with respect to the y-axis. Everybody see that there? Symmetry with respect to the y-axis. And that's exactly what was shown algebraically, that we did have y-axis symmetry because we were able to get back the original equation after simplifying. Okay. So yeah, the graph is symmetric with respect to the y-axis. Make sense? All right, so this is how you test for different symmetries, okay, with respect to the x or y axis or the origin. Another thing of interest in higher level math, when you get into advanced series work, is whether a function is odd or even, okay? Well, what is the definition of an even function? Well, ladies and gentlemen, we say that a function that is symmetric with respect to the x-axis is an even function. And the technical definition of an even function is to say that we take some function f of x and evaluate it at negative x, we're always going to get back the function evaluated at positive x. And that's true for all x. If that's the case, then we have what's called an even function. And even functions are always symmetric with respect to the y-axis. Notice that. Okay. So even functions are always symmetric with respect to the y-axis. And this is the definition of what it means for a function to be even. If you evaluate a function at negative x and get back the function value at positive x, it's an even function. That's an even function. What's an odd function? Okay. Well, ladies and gentlemen, an odd function is any function that is symmetric with respect to the origin. Any function that is symmetric with respect to the origin is an odd function. Or technically, it's saying a function f of x is odd if we, for all values of x, evaluate the original function at negative x, and we keep getting back the opposite of the function evaluated at positive x. That's to say that the function is odd. But just remember, odd functions are origin symmetric. Okay. All right. So what it means, let's see if we can go back to section 2.7. Oh, it timed me out. I hate that. Okay. All right, so odd or even. Let me give you a function to work with, and let's try to determine if it's odd or even here. Suppose I have y is equal to negative 2x to the fourth plus 5 times the absolute value of x. Let's see if this function is odd or even. Well, one way to determine if it's odd or even is to graph it real quickly using a graphing utility. And then to see if it's symmetric with respect to the y-axis. If it is, it's an even function. If it's symmetric with respect to the origin, it's an odd function. Suppose we don't have a graphing utility, we can't graph it. Well, there's another way. So, ladies and gentlemen, instead of calling y our output variable, we'll call it f of x. So therefore, we'll call the function f of x equals negative 2x to the fourth plus 5 times the absolute value of x. So let's test and see if this function is even. If it's an even function, it must be true then that f evaluated at negative x must be equal to f of x. Let's see if that's true. So I'm going to replace x with negative x. I'm going to put negative x everywhere in where I see x in the definition of this function. So we got negative 2 times negative x to the fourth power plus 5 times the absolute value of negative x. And now I'm going to simplify this. Negative x to the fourth power, do you agree, is going to be positive x to the fourth? When you raise a negative to an even power, you get a positive. So this is going to be x to the fourth times negative 2 is still negative 2x to the fourth. What's the absolute value of that negative x? Do you agree that's the same thing as the absolute value of positive x? Hey, but isn't this, ladies and gentlemen, my original function f of x? And there you go. We have shown, therefore, that f of negative x is equal to f of positive x. And this is true for all x. So f of x is what? Is it even? It is an even function. It's an even function. And so therefore, if we were to look at the graph of this function, we would suspect that it's going to have to be what? Symmetric with respect to the y-axis. So this is y-axis symmetric. Y-axis symmetric. And we could use our, our graphing calculator to quickly graph this function here and check it out and see what kind of symmetry it has. So hit y equals. Let's type in that function. So we got negative 2x raised to the fourth power plus 5 times the absolute value of x. The absolute value function is in the math menu. Hit math, go over to number, and it's the ABS function. Math, number, ABS, absolute value of x. All right, hit your graph button, ladies and gentlemen, and let's see if this graph is symmetric with respect to the y-axis. Does it look like that graph is symmetric with respect to the y-axis? Wait a minute. I'm sorry. Did I do a screen share? Okay, I'm sorry. Can we see that, ladies and gentlemen? I graph our function here. And this is the graph. Does it look like it's symmetric with respect to the y-axis? It certainly does. And therefore, that confirms our suspicion that it is an even function. And we determined what it was even algebraically by showing that f of negative x is equal to f of x. Okay. Try another one. Suppose we have f of x is equal to 4x cubed minus x. Let's see if this function is even. Is this an even function? Well, if it is, then f of negative x has to be equal to f of x. So let's evaluate our function at negative x. Put negative x in for x everywhere. And now we will simplify this. What's negative x times negative x times negative x? That gives you negative x cubed. And negative x cubed times 4 is negative 4x cubed. What's the negative or the opposite of a negative x? Positive x? Ladies and gentlemen, when I simplify this, do I get back my original function, f of x, which is 4x cubed minus x? Is this the original function? this is not equal to the original function. So therefore, this function is not even. Because I was unable to show that f of negative x is equal to f of x. In fact, f of negative x is not equal to f of x. So it's not an even function. Okay, if it's not even, how about, is it odd? Is it an odd function? Well, to show it's an odd function, we need to show that f of negative x is equal to the negative of f of x. So f of negative x, we already did f of negative x. F of negative x is negative 4x cubed plus x. Is this, ladies and gentlemen, by chance equal to the opposite of f of x? Is that true? In other words, is this equal to the opposite of f of x being 4x cubed minus x? Is that true? In other words, is this equal to, distributing the negative sign inside the parentheses, negative 4x cubed plus x? Is that true? Well, I'll be darned, it is. So f of negative x right here is equal to the negative of f of x. So therefore, we have shown that f of negative x is equal to negative of f of x for all x. And therefore, the function is odd. This is an odd function. Okay. And another way to confirm that it's an odd function is to graph the function and see if it is symmetric with respect to what? An odd function must be symmetric with respect to what? The x-axis, the origin? Which one is it? Do you remember? I believe it's the origin, correct? So let's just go off to our graphing calculator and graph 4x cubed minus x. So go to your equation editor, clear out any garbage, type in 4x cubed minus x, hit graph, and let's see, does it appear this graph is symmetric with respect to the origin? What do you think, ladies and gentlemen? Symmetric with respect to the origin? In other words, if I choose a point on this graph, which looks like 1, -2, I'm sorry, 1, 2, is the point -1, -2 also on the graph? 1, 2 is on the graph. Is -1, -2 also on the graph? It looks like it. Sure it is. It's right there, correct? You could even look at the table of values. Second graph gets into your table here. I don't even like that setting there. That's an awful setting there. Hold on a second here. Let's go with this. Let's just look at this, ladies and gentlemen. Look at, for every point x, y that's on the graph, if negative x, negative y is on the graph, then the graph is symmetric with respect to the origin. 1, 3 is on the graph. So is -1, -3 on the graph? Yes. 2, 30 is on the graph. So is -2, -30 on the graph? Yes. 3, 105 is on the graph. So is -3, -105 on the graph? Yes. This graph is symmetric with respect to the origin, and therefore it's an odd function. Does that make sense? It's an odd function. All right, that's an odd function there. All right. The last thing that we're probably going to have time for here in section 2.7 is to go over something called a piecewise function. And piecewise functions are encountered all the time, especially in calculus, especially your first semester of calculus. You work with piecewise functions when dealing with the concept of continuity or limits, okay? And so we are going to address what a piecewise function is in mathematics. Piecewise function. Here's an example of a piecewise function. F of x is equal to, now the definition, piecewise functions have multiple definitions. So this piecewise function has a linear definition for input values that are less than -1. This piecewise function takes on the definition of this constant function, f of x equals -3, for input values that lie between 2 and -1. This piecewise function takes on a definition of a radical function, a square root function, for input values that are greater than or equal to 2. So suppose I want you, using this piecewise function, I want you to find f of -3. Well, I have a question for you, ladies and gentlemen. Which definition are we to use? The first, second, or third, if I put -3 into this function? Well, you got to ask yourself, in what interval is -3 found in? What interval is -3 found in? Is it found in the first interval, the second interval, or the third interval? What interval is positive -3 found in? Is -3 greater than or equal to 2? No, we don't use this definition. Don't use this one. Is -3 between -1 and 2? No, so we don't use the second definition. Is -3 less than -1? Yep. And so therefore, to evaluate the function at -3, we must use this linear definition. So therefore, f of -3 is going to be the opposite of -3 minus 1, which is to say 3 minus 1, which is 2. That's what f of -3 would be, is 2. Let's evaluate this function at -1. If I put -1 into this function, in what interval is -1? The first, second, or third? -1. Is -1 less than -1? No, don't use this definition. Is -1 in this interval? Is -1 greater than or equal to itself?
Yes.
And at the same time less than 2? Yes. Since -1 is in this interval, we use this definition. So f of -1 is equal to -3. There's your answer. Let's try another one. Let's evaluate this function at 2. In what interval is 2 found? First, second, or third? Is 2 less than -1? No. Is 2 between -1 and 2? No. Is 2 greater than or equal to itself? Yes, 2 is equal to itself. So 2 is found in this last interval, meaning we must use the last definition to compute the output value of this piecewise function. Therefore, f of 2 is going to be the square root of 2 minus 2, which is the square root of 0 or 0. Okay. All right, f of 6. What definition do I use to evaluate the function at 6?
The last one.
Yep, because 6 is in the last interval. 6 is some number greater than or equal to 2. Therefore, to compute the output of f of 6, we must use the last definition, which is to say f of 6 is the square root of 6 minus 2, which is to say the square root of 4, which is to say 2. And there you go. We call it a piecewise function because the domain of this function is broken up into 3 different pieces or intervals. This interval, or this interval. Okay? And that's why it's called a piecewise function. I like to think of piecewise function as being kind of like switch functions. Kind of like you got a main track coming into a railroad yard. You got a track that goes off this way, one that goes straight ahead, and then one that goes this way. Okay? Depending upon what the input is, ladies and gentlemen, will dictate as to what track we switch the train onto. You agree? Same thing here. Depending upon what input we put into this function, what interval the input lies in, will dictate which definition we are to use to compute the output value. All right? That's called a piecewise function. How would we graph this piecewise function here? How would we graph it? Well, this is how we're going to graph it manually. All right? We're going to have to graph 3 different definitions of this function. And then, ladies and gentlemen, we're going to have to erase portions of the graph so that it is only valid for certain input intervals. All right, so let's show you how to graph this function manually here. First, we're going to graph the first definition. we're going to graph f of x equal to negative x minus 1. But this is a linear function. And what form is this linear function in? Do you recognize that it's in what? Y equal to mx plus b form? That's slope-intercept form. So what's the slope of this line? The slope is, yeah, slope is -1. My y-intercept b is also what? -1, correct? So here's what I'm going to do. To graph that, I'm going to get a piece of graphing paper. I'm going to get a piece of graphing paper here. And we're going to graph that line. So y equal to negative x minus 1 is easy to graph because we know the y-intercept is -1. So I'm going to plot the y-intercept right there. And then my slope is -1. So the slope being -1 says for every 1 unit I go down, I would go 1 unit to the right. So starting at my y-intercept, if I go down 1 unit and 1 unit to the right, I plot another point. Let's do that again. Down 1, 1 to the right, plot point. Down 1, 1 to the right, plot point. So now I'm going to take a ruler and put a line to these points. And we have the graph of that first definition of this piecewise function. F of x equals negative x minus 1. Oh, but wait a minute. We cannot continue to keep this entire graph because we need to understand, ladies and gentlemen, that this linear definition of negative f of x equals negative x minus 1 is only valid for input values that are less than -1. So we're going to have to erase the graph of this first definition for any input values that are -1 or larger. So we got to go to our graph here, and we have to realize that this graph is only going to be visible for input values that are less than -1. For less than is only going to be visible for input values of x less than -1. So I'm going to have to put an open circle here at x equals -1. And the only portion of this graph you're going to see is the portion of the graph that is valid only for input values of x that are less than -1, which is over here. Nowhere are you going to see this graph for input values of x that are greater than or equal to -1. So we have to erase this entire branch of the graph. So we take an eraser, or in my case, I take my white out and I get rid of this branch. It's gone. Got to erase it. And you are looking at the graph of the first definition of that piecewise function. That's the only part you're going to see of it because it's only valid for x less than -1. Now we got to graph the second definition, which is to say f of x equals -3. But what is the graph of f of x equals -3? F of x equals -3 is going to be what kind of a line? Well, if I said graph y equals -3, what kind of line is that going to be? It's just going to be a what? A horizontal line? Just a horizontal line that goes through the y-axis at what? At -3? That's all it is. So let's take a ruler, put a horizontal line through the y-axis at -3, -1, 2, 3. There it is. But will I see this entire line on the graph? The answer is no, because f of x is only equal to -3 for what kind of input values of x? F of x is only equal to -3 for input values of x that lie between -1 and +2. That's it. That's the only portion of this horizontal line you're going to see is on this interval here, -1 to 2. So for x equal to -1, greater than or equal to -1, up to but less than 2. Open circle right here. This is the only portion of that horizontal line we're going to see because that's the only portion or the interval on which this definition is valid from x equals -1 up to +2. So we have to erase. We got to erase the graph outside of that interval. This has to go. That's gone. And we also have to erase this portion here. This has to go too. And you have the graph of the second definition of that piecewise function. Finally, we have to graph the last definition, which is to say f of x is equal to the square root of x minus 2, only valid, however, for input values of x that are greater than or equal to 2. But I have a question for you, ladies and gentlemen. What is the basic parent function for this function here? The basic parent function. It's just f of x equal to what? The square root of x? Do you agree? So what is the graph of the basic square root function y equals the square root of x? That's just going to be, remember, and that's why I want you to memorize those graphs from that table that open up 2,6. This graph is just going to look like that. Do you agree? The graph of the basic square root function. But the function we need to graph is the function which is the square root of x what? Minus 2. So what kind of a transformation has occurred from here to here? What's happened? What's happened? Vertical translation, horizontal translation, reflection, stretching, shrinking vertically, horizontally. What's going on here?
Horizontal 2 to the right.
That's right. It's been the graph of the basic square root function has been shifted 2 units to the left. So this thing's got to go 2 units to the left over here, 2 units to the left. So let's do that. So 2 units to the left. So that means the graph of the basic square root function here is going to go what? 2 units to the what? Left. So -1, -2. So that graph is going to look like what? It's basically going to look like this. But later on, we cannot keep that entire graph because this definition of the square root of x minus 2 for f of x is only valid for real number inputs that are greater than or equal to 2. That's it. So we're only going to see the portion of this graph for input values that are 2 or larger. 2 or larger. Okay. And so where is this graph going to be? For x that is 2 or larger. Well, if I actually put 2 into this function here and evaluated the function at 2, I would have the square root of 2 minus 2, which is what? 0. So we should have the point 2, 0 that lies on our what? Lies on our graph, correct? Okay, so what is going on here? Wait a minute. We shifted this the wrong way. Ladies and gentlemen, f of x minus 2 should have the graph be shifted 2 units, not to the left, but to the what? Should have went 2 units to the right. No wonder there's a problem here. This graph don't go 2 to the left. It goes 2 units to the right. It should be over here. It's not this one. It's just this one. All right, so this is not right. Hold on, I got to erase this. This all has to go. That's not correct. All right, so it should be our basic square root function of x shifted 2 units to the right. So originally it started at the origin and went this way, but now we got to shift this point 2 units to the right, so it has to go here. And then we're going to go like this. And there you go. You are looking at the graph of that piecewise function. Okay, it comes in 3 pieces. This is the graph of the linear part of the piecewise function for input values that are less than or equal to less than -1 rather. That's why it's an open circle. This is the graph of the function, the constant portion of the function f of x equals -3 for values of x that are between -1 and 2. Including -1, hence closed circle here, but open circle here. And this would be the graph of the portion of the function for values of input values of x that are greater than or equal to 2. Hence we have a closed circle there. So there you go. That's how you would graph a piecewise function, kind of like manually. You just graph every definition in its entirety and then erase the portion of the graph that you would not see that conforms to the interval of the definition being valid. Okay, and that's how you graph a piecewise function. All right, so all right, one last classwork, ladies and gentlemen. We'll call this classwork what is it, 2? I'm going to give you a piecewise function here. F of x is defined to be this function, x plus 3, valid for x less than -1. And it's going to be x equal to x squared for values of x that lie between 2 and -1. I want you to, in A, I want you to find f of -10. B, I want you to evaluate this function at -1. C, I want you to evaluate this function at, let's say 1. And D, I want you to evaluate this function at 6. Okay? Go ahead and see if you can do those quickly for that piecewise function. This will be the last classwork today, and this is all I can cover today. I'm all out of time. So just see if you can find the value of all these functions using that piecewise defined function there. Shouldn't take too long because these are very easy to evaluate. These definitions are pretty simple. Okay. All right, so what's f of -10 going to be? Anybody? What definition should I use? First or second? First definition or second definition?
The
First.
first one.
Yeah, -10 is not in this interval, but -10 is a real number less than -1. Because of that, we have to use the first definition. So f of -10 is going to be -10 plus 3, which gives you -7. Your answer, f of -10, should be -7. Finally, and now we put -1 into my function. Which definition am I to use? In which interval is -1 found? The first or the second interval?
Second.
Second.
It's not in this interval. -1 is not less than itself. It is equal to itself. -1's in this interval. We must use this definition. So f of -1 is to say -1 squared, which gives you a +1. Therefore, we would expect -1, 1 to be a point that lies on the graph of this piecewise function. F of 1 would have me using what definition? First or second?
Second.
Yeah, 1 is not in this interval, but 1 is between -1 and 2. So being in this interval, therefore, we have to use this definition. So f of 1 would be 1 squared, which is 1. 1, 1 would have to be a point that's on the graph of this piecewise function. And now comes the tough one. Ladies and gentlemen, what's f of 6? Anybody gets up for this? In what interval is 6 found? Is it found in this interval? No, 6 is not less than -1. Is 6 between -1 and 2?
No.
No, 6 is not in this interval, is it? 6 is not in here. In fact, ladies and gentlemen, there is no definition for this function for values that are greater than or equal to 2. So we would say this is undefined. Undefined, because there's no definition for what it should be. If we choose values and put values in this function that are greater than or equal to 2, there's no definition for the function. Undefined. There you go. I'm all out of time. I'll have to finish this section next week. I will update Alex, ladies and gentlemen. And if you have any questions, I'll be on the line for a couple minutes. If not, have a great weekend.